Hello friends, welcome back. In this video, we will continue our discussion on VXLAN technology, and more specifically, we will discuss about VXLAN Flood and Learn. So like we discussed in VXLAN, BGP, L2VPN, EVPN, VXLAN stands for Virtual Extensible LAN or Virtual Extensible Local Area Network. It is a layer 2 and layer 3 overlay tunneling protocol, specifically an Ethernet in UDP and UDP in IP tunnel. The main objective of this technology is to provide layer 2 extension across two data centers. For example, we could use this technology to perform vMotion across two DCs or two separate facilities or sites owned by a customer. It is a standards-based implementation, and technologies like VMware, NSX Automation, and Cisco ACI are both running VXLAN behind the scenes, and it is supported by all major vendors like Arista, Cumulus, etc. VXLAN is a replacement for VLANs. As we know, with VLANs, we use 12-bit space, which allows for just over 4,000 VLAN IDs. Whereas with VXLAN, we use 24-bit space, which allows for just over 16 million values. The big change with VXLAN is that it allows for layer 2 multipathing. So it does not need STP for loop prevention. And in terms of topology, it uses cross fabric logic, which is very similar to fabric path, which is the leaf spine topology. And in terms of the underlying architecture, VXLAN uses IP for transport. So there is no special connectivity requirement for VXLAN. So a private on-prem DC could be connected to a public cloud platform like Amazon, Azure, Rackspace over regular internet transport because there is no special requirement for VXLAN. So as long as there is IP connectivity between the VTEPs, we could establish VXLAN tunnel over it. So with VXLAN, there is no specific hardware vendor dependency, or you're not logged into any hardware vendor, like in the case of Fabric Path. And as discussed earlier, it does not break layer 2 adjacency requirements and allows for multi-tenancy. So it provides separation of customer traffic over shared underlay fabric. So it allows for overlapping layer 2 and layer 3 addresses, which makes the VLANs and IP subnets as locally significant. So friends, let's now discuss some important VXLAN terminology. First of all, we have the underlay network. This provides the transport for VXLAN and facilitates the tunnel establishment between the various VTEPs. So there are three main protocols that we need to run in the underlay network. First, we have the IGP routing. So we could be running OSPF, ISIS, EIGRP, or even static routing. So as long as the two VTEPs that will be establishing the VXLAN tunnel, they could ping each other and there is IP reachability, that's all is required to establish the VXLAN tunnel. And then we need the multicast routing. Specifically, we need PIM. This is required for the BUM traffic or the broadcast, unknown unicast, or multicast traffic, like the R packets, for example. And then we have the BGP routing. But this is not applicable when using VXLAN Flood and Learn, because in VXLAN Flood and Learn, we learn the remote MAC addresses in data plane as compared to BGP routing, where the remote MACs are learned in control plane. And then we have the overlay network. So this is the actual VXLAN service that is provided by this technology, or more specifically, it is the tunnel that is created between the two VTEPs. And speaking about VTEPs, it stands for VXLAN Tunnel Endpoint, or to be precise, it's the box or the device that is encapsulating and decapsulating the VXLAN traffic. And VTEPs could be either hardware or software based. The next term that we need to understand is the VNI or VNet. It's also called VXLAN Network Identifier. So the terms VNI and VNet could be used interchangeably. So VNIs or VNets, they replace the VLAN ID in classical Ethernet terms, and it is the mapping between the VLAN ID and VXLAN network identifier or VNet. Then we have the VXLAN segment, so it is the resulting layer 2 broadcast domain that is formed as part of extending layer 2 across the layer 3 underlay network. And then we have the VXLAN gateways. So they are the devices that forward traffic between VLANs. It can be either at layer 2 and layer 3. Then we have the network virtualization edge. They are the logical representation of the VTEP device. So from a configuration point of view, NVE is the tunnel interface. So when we configure VXLAN on the VTEP, we configure it as interface NVE1. So let's understand the basic workflow for VXLAN traffic. So here we have a simple topology where we have three hosts. We have VLAN 10 client 1, VLAN 10 client 2, and VLAN 20 client 1, and they are connected to leaf 1, leaf 2, and leaf 3 respectively. So let's assume that VLAN 10 client 1 wants to ping VLAN 10 client 2. They are in the same VLAN and in the same subnet. And as this is the first time VLAN 10 client 1 is trying to communicate with VLAN 10 client 2, there is no ARP entry for VLAN 10 client 2 in the ARP cache of VLAN 10 client 1. So leaf 1 will receive this ARP request from VLAN 10 client 1, and it will forward that ARP request to all the active ports in VLAN 10 configured locally. And as we will have a multicast group mapped to the VNI on the leaf switch, the leaf switches will also forward the ARP request as a multicast packet to the multicast group configured for that particular VNI. So from a configuration perspective, a VLAN will be mapped to a VNI or a VNID, and under the NVE interface, we will also configure the VNI or map the VNI to a multicast group. And this is done specifically for bump traffic, that is broadcast, unknown unicast, and multicast traffic. So unicast packets are sent as unicast, broadcast packets are sent as multicast, unknown packets are sent as multicast, and multicast packets are sent as multicast. So once the remote leaf, which has VLAN 10 client 2 attached to it, once it receives the ARP request, it will forward the ARP request to VLAN 10 client 2. And once it receives the ARP reply, it will be sent as a unicast packet to leaf 1. And leaf 2 now has a MAC address entry for VLAN 10 client 1 in VLAN 10, but the interface won't be a local interface, it will be a VTEP, and the address for that VTEP will be leaf 1, which is 3.3.3.3 in our case. And we will configure and verify the whole process step by step when we go over the lab section. And the whole process will be much clearer when we have a look at the configuration and then also the Wireshark captures. So once the remote VTEP has been discovered, any subsequent traffic will be sent as unicast encapsulated with VXLAN ID or VNID. And the important thing to remember is that both VLAN and VXLAN headers do exactly the same thing. They are both tags in the data plane, which is used as an indicator to the remote VTEP, which indicates the remote VTEP in regards to which MAC address table or VLAN the traffic belongs to. So friends, let's now go over VXLAN Flood and Learn configuration from a Cisco Nexus perspective. And for Nexus 5600, when it is used as a hardware VTEP, we need to change the switching mode to store and forward. So before we start planning for VXLAN on a Nexus 5600 platform, we need to run this command, which is hardware Ethernet store and forward switching. And once we have applied this config, the switch needs a reboot. So this is something which must be considered before you start rolling out VXLAN on Nexus 5600. So now that caveat is out of the way, so let's discuss the first requirement, which is IP unicast reachability between the VTEPs. particularly the VTEPs must be able to reach each other on their loopback IP address, which will be used as the source of the VXLAN tunnel. So going back to our topology, we have the three leaf switches, leaf 1, leaf 2, and leaf 3, connected to the two spines, spine 1 and 2. And like discussed earlier, we have spine 2 running as the rendezvous point as we are running multicast IP PIM sparse mode. So we have configured OSPF as the underlying IGP or the underlay IGP. So leaf 1 should now be able to ping leaf 3, sourcing the traffic from its loopback interface. So if I have to ping 5.5.5, source 3.3.3.3, yeah, we have IP reachability. So leaf 1 can now ping leaf 3, and let's check leaf 2 as well. So yeah, we have IP reachability between the VTEPs or the leaf switches, and we also need to make sure that we have configured the rendezvous point on the leaf switches. In our case, we will be doing a manual or static configuration of RP on the leaf switches, and it's a one-line configuration here. So we configure spine 2 with the IP address of 2.2.2.2 as the rendezvous point on all the leaf switches. So we have that on leaf 1, leaf 2, and leaf 3. The next step will be to enable the relevant features on all the leaf switches, and more precisely, the features that we need is the feature NV overlay, which is used to facilitate, or it allows the creation of the NVE interface on the Nexus platform. And the next feature that we need is the feature VN segment VLAN based. So this is the feature which allows the VLAN to VNI mapping. So if we jump back to our leaf switches and have a look at the features enabled, we could see that we have the feature NV overlay and feature VN segment VLAN based enabled on all the leaf switches. So we've got the features enabled on leaf 1, leaf 2, and leaf 3. So we've got feature NV overlay and feature VN segment VLAN based. So the important thing to consider is the order in which we enable these features. So we must enable NV overlay before we enable feature VN segment VLAN based. So the next step in the configuration process is to map the VLANs to VXLAN IDs or VNIDs. And the way we do it is that we go under the VLAN configuration mode. So in our case, we go to VLAN 10 and the command is VN segment. So we create a one-to-one mapping between the VLAN ID and the VNI or VNID, which is the VXLAN network identifier. So now it's the VNID which becomes globally significant, and it's this value which must match between the leaf switches. So we can have VLAN 10 mapped to VNI ID or VNID 10,010 on leaf 3, and we can have VLAN 20 mapped to VNID 10,010 on leaf 1, and as they are in the same subnet, they should still be able to communicate with each other at layer 2. And that is because they share the same VNI ID or VXLAN network identifier and are in the same broadcast domain. So we will do the same on leaf 1. So VN segment 100,010 or 10,010. And likewise, we'll go to leaf 2 under the VLAN configuration mode, VN segment 10,010. The next step will be to create the network virtualization edge interface or the NVE interface. This is the logical representation of the VTEP device in the VXLAN network. From a configuration point of view, the way we create the NVE interface is to go to the global config mode, then the command is interface NVE1. We will no shut the interface, and like we do in the case of any other tunnel interface like a GRE tunnel, we need to specify the source of the VXLAN tunnel interface or the NVE interface. So the command would be source interface loopback 0. So we created the interface NVE1. We also specified the source for this VXLAN tunnel interface. The next thing that we need to configure is the membership or the traffic that needs to be allowed over the VXLAN tunnel interface, and we do that by specifying the member VNI. So in our case, the member VNI was 10,010, so that's what we defined under VLAN 10. And as we discussed previously, we also need to define a multicast group address under the member VNI for our bump traffic. So we configure the member VNI, and now we will configure or map the multicast group with this member VNI. And the multicast group that we will use for this VNI is 239.0.0.10. So let's take a quick look at the configuration for the NVE interface on this leaf switch. So we've got the source configured, we've got the member VNI, and we also have the multicast group mapped to this member VNI. And before we configure the NVE interface on leaf 2 and leaf 3, let's quickly configure an interface VLAN 10 on leaf 1 and make sure that it can communicate with VLAN 10 client 1 locally. So this is to make sure that there is communication between VLAN 10 client 1 and leaf 1 in the local segment. So we have the interface Ethernet 1.1 configured on VLAN 10 client 1. That's the interface on which we have an IP configured for VLAN 10 client 1. And the IP we've used is 192.168.10.10. And we have an SVI configured on leaf 1 for VLAN 10, and the IP address we've used is 192.168.10.1. And just to make sure that there is local communication between leaf 1 and VLAN 10 client 1. So yeah, we've got layer 3 communication between leaf 1 and VLAN 10 client 1. And likewise, we will make sure that there is layer 3 communication between leaf 2 and VLAN 10 client 2, as VLAN 10 client 2 is attached to leaf 2 in our topology. So yeah, there is communication between leaf 2 and VLAN 10 client 2. So now we will initiate a ping from VLAN 10 client 1 towards VLAN 10 client 2. And just to make sure you have it right, we've got the IP addresses as 192.168.10.10 and 192.168.10.20 for VLAN 10 client 1 and VLAN 10 client 2 respectively. So now let's initiate a ping from VLAN 10 client 1 to the IP address of VLAN 10 client 2, which is 192.168.10.20. So as soon as we initiated a ping from VLAN 10 client 1 towards VLAN 10 client 2, it sent an ARP request as we see here. So we have the sender MAC address, which is the MAC address of the interface that VLAN 10 client 1 will use to form this ARP request. So in our case, which will be interface ETH11, and as you see, the MAC address for that interface ends with 1B08, which we can verify on the Wireshark capture. And the sender source IP address is 192.168.10.10. The target MAC address for an ARP request is all Fs, as we know, and we have the target IP address of VLAN 10 client 2, which is 192.168.10.20. And as this is an ARP request, it will be sent to the broadcast address of all Fs, as we could see on the Wireshark capture. So now we will encapsulate the ARP request in VXLAN header. So we have the VXLAN header here, and specifically what we're looking at is the VNI header or the VNI value, which is 10,010, and it gets encapsulated in UDP with a destination port of 4789. That's the well-known port for VXLAN. And then we have the outer IP header, where we use the source interface of the VXLAN tunnel, which is 3.3.3.3 in our case. And going back to the topology, 3.3.3.3 is the loopback 0 interface of leaf 1, which we configured as the source interface for interface NVE1 or the VXLAN tunnel interface. And the destination for this IP header is the multicast address of 239.0.0.10, And if you remember correctly, or if we go back to the configuration on leaf 1, so that's the multicast group address we configured under member VNI to ensure that any bump traffic will be forwarded to that multicast group address. And as we have the same multicast group address configured on leaf 2, it will listen for any traffic destined to that multicast group address, and as and when it receives any packet for that multicast group address, it will decapsulate that packet and perform a VXLAN to VLAN mapping. And as this is an ARP request, it will send or forward that ARP request to all the interfaces that are participating in that particular VLAN. So if we check the MAC address table for VLAN 10 on leaf 2, we could see that it has learned the MAC address for VLAN 10 client 1 on its NVE interface and with the loopback 0 IP of leaf 1 as the next hop, which is 3.3.3.3. And now when VLAN 10 client 2 sends the ARP reply as a unicast, so we have the sender MAC address here, sender IP address, the target MAC address, which is the MAC address of the originator, which was VLAN 10 client 1 in our case, and the target IP address of VLAN 10 client 1. So it is sent as a unicast packet. And if we look at the outer header, so the traffic can now be sent as unicast from leaf 2 straight to leaf 1. So as we see, this is encapsulated within VXLAN, which gets inside of UDP and which gets inside of IP. So leaf 1, when it gets the ARP reply from VLAN 10 client 2, it creates a mapping for that remote host in its local MAC address table, and the remote port being the NVE interface with the remote IP being the loopback 0 or the VXLAN tunnel interface of leaf 2, which is 4.4.4.4 in our case. So now that we have gone over the ARP request and response packets, let's see if VLAN 10 client 1 and VLAN 10 client 2 can ping each other. Yep, now they can ping, so there is two-way communication. And as you can see on the screen, these are some of the important verification commands for VXLAN Flood and Learn. And from a data plane perspective, the most important being the show MAC address table. And we can also check the remote peer mapping on the local leaf switch and also the VNIs that we are listening for. So let's say if we run the command show NVE peer, it tells us the remote VTEPs that we have learned on this local switch and how we've learned it. So we've learned 4.4.4.4 as data plane, and then if we run the command show NVE VNI, so it will tell us the VNI that this local leaf switch is listening for and the mode, which is data plane DP. If we were to be using BGP as the control plane, then we'll have the mode as CP, and then we have the type, which is L2, and then we have the broadcast domain or the VLAN ID in our case, which is VLAN ID 10. It also shows the multicast group that this VNI is mapped to. So as we have seen, we now have IP reachability between VLAN 10 client 1 to VLAN 10 client 2, and both of these client devices are in the same subnet, so they communicate at layer 2 over a layer 3 VXLAN underlay network. So friends, this was a very detailed / very practical level explanation and configuration of VXLAN Flood and Learn technology. If you do like this video, please hit the like button, comment and subscribe to my channel. And if you have a feedback, good or bad, please leave it in the comment section. So friends, thank you very much for your time today. And until next time, see ya. Take care.